Tonight, we are very fortunate to have our speaker, Professor Daniel Whiteson from the University of California, Irvine. Daniel graduated with his PhD from the University of California, Berkeley in 1998, only 20 years ago. Okay. So he worked on this, the D0 experiment at Fermilab Tavitron Collider. Now he's a member of Atlas experiment at the Large Hadron Collider, which is the LHC, and at CERN, Geneva. With his outstanding research, he has won numerous awards and honors, including a Fulbright Fellowship at the Niels Bohr Institute, Copenhagen, Denmark, and Department of Energy Outstanding Junior Investigator Award, Alfred Sloan Foundation Fellowship, and UC Irvine Chancellor's Awards for Excellence in Fostering Undergraduate Students. And he became a full professor in the year for 2016. Humanity's understanding of our physical world is full of gaps. It's not only just a little bit tiny, small gaps that you can easily ignore. In fact, there are huge yawning voids in our basic notions of how the world works. Daniel will explore everything we don't know about the universe, the numerous holes in our knowledge of the cosmos. Using cartoons drawn by PhD comics creator Jorge Cham, and Daniel will give us the best answers currently available for a lot of questions that are still perplexing scientists, including questions about dark matter and dark energy, and even the nature of space-time itself. The universe is full of weird things that sometimes don't seem to make sense to everybody. However, the questions we cannot answer are as interesting as the ones that we can. So Danny invites us to see the universe as a possibly boundless expanse of the uncharted territory that are still ours to explore. Based on his recent book, co-authored with Jorge Cham, and the title of his lecture today is We Have No Idea. The exploration of the unanswered questions about our universe. So please join me to welcome Professor Daniel Whiteson for the lecture.
Thank you very much, Tao, and thank you very much to the committee for inviting me. And mostly thank you to all of you for coming out on this evening to hear a physics lecture. I just flew in, so it's wonderful for me to escape the oppressive sunniness of Southern California and appreciate some gray sky and flitting snowflakes. So thank you for coming out on a cold evening. So indeed tonight I want to talk to you about an idea and a feeling and a sort of personal view I have about what's exciting about science and the universe. And that's also the focus of the book. It's called We Have No Idea. And in my view, we don't spend enough time in science talking about all the things that we don't know, embracing our cosmic scientific ignorance. And so that's the point of the book. And the book, I think, is unusual in two ways. One is that it focuses on what we don't know, and I'll get into all that in just a moment. But also that I have this co-author here, Jorge Cham, and together we wrote a book that contains not just physics, but also a bunch of cartoons. You can see his fantastic doodles here, and they're all throughout the book. And the goal there is to try to use cartoons to describe physics in a way that's not intimidating and that's very accessible. And let me tell you first a little bit about how Jorge and I started working together, because it's a fun story, and then I'll dig into the content of the actual book. So for those of you who don't know, Jorge is a famous online cartoonist. He writes a website called PhD Comics, and the comics focus on the travails of graduate students and the frustrations of research, and often they're making fun of what it's like to be a graduate student, or how badly graduate students get treated by their professors. And wherever I go around the world, I visit physics labs here and there's always one of his cartoons up on the wall. And usually it's one, like this one, that makes fun of the professors. And when we travel around, we talk about our book, there's always some graduate student that comes up to Jorge and says, Jorge, if it hadn't been for you, I wouldn't have known that everybody felt the same way I did about research. And so he sort of conducted like group therapy for the whole community, right? The funny thing for me is that I've been reading his cartoons since I was in grad school, And I can go back and look at the same cartoons, which I used to identify with the graduate student in it, and now I look at it as a faculty member, I'm like, yeah, I sort of see the other side of that issue. Anyway, it's a lot of fun. And Jorge has ventured beyond just making comics. He also does some science communication, explains complex topics using cool diagrams, etc. He's a real artistic gift. So about 10 years ago, I was thinking about how to communicate science to the public, what would be a good way to do it. And I read this cartoon, this comic book about Google Chrome, this browser. Somebody put out a cartoon about the development of this browser. And I'm not very interested in how you write a browser, but this comic book was really fascinating. And I thought, if somebody could take development of a browser and make it fun to read, then certainly we could do the same thing for physics. But the problem is, I don't have any artistic skills myself, so I couldn't draw this cartoon myself. So I was talking to my wife about this idea. She's also an academic and a huge fan of Jorge's, and she said, ooh, why don't you email Jorge Cham and get him to do it? And Jorge's like a famous celebrity, so I thought, sure, and then after that I'll email Brad Pitt, right? And maybe we could do a movie together, right? Anyway, I took her up on her suggestion, and here's the actual email I sent Jorge like 10 years ago. And I'm like, blah, 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 blah. Here's all the exciting things about it. He actually wrote me back. And I think the reason he wrote me back was because of this one word in the email. See, Jorge puts his cartoons online for free, and mostly he gets inundated with people asking him to do work for free. So when I suggested I would actually pay him to do these cartoons, he was pretty excited. And it turns out that he doesn't live too far from me. And so he came down to the UC Irvine campus, and we spent a day talking about all the exciting physics and science, and that's his drawing of me waving my arms in the air as I'm talking, which is pretty accurate. And out of that came some fun comic videos describing what is the Higgs boson, or what is dark matter, or what are gravitational waves. And they were a lot of fun, and they went sort of viral and went everywhere, which was fun to see. And they were picked up by CBS News and New York Times, and we got a lot of attention for it, which was a lot of fun. Maybe my proudest moment for this project, though, was when we actually discovered the Higgs boson in 2012, and then the following year they awarded the Nobel Prize for the idea of the Higgs boson. Right? And every time the Nobel Prize is awarded, they put out some information. Here's the theory, here's what it is, here's why it's important. And at the bottom, they have this section called Further Reading. Right? And in this section called Further Reading, boom, there was a reference to our comic. And I thought, this might be the only time the Nobel Prize Committee ever cites my work, but, if it has to be for cartoons, I'll take it. That's fine with me. All right. So we had a lot of fun working together, and we were talking about the general idea of physics and explaining it to the public, and that's when we decided to write this book called We Have No Idea. And for those of you guys are a smart crowd, you probably read a lot of popular science books. This is a popular science book, but it's different from most science books because it's not about what science has learned, right? It's not about all the amazing things that science has figured out. It's about all the things we don't know about the universe. So if you come to hear a lecture by somebody, talking about their popular science book, you expect them to be an expert, right? You hear about a book about evolution, you want to hear from an esteemed biologist, right? So if this book is about not having ideas and not knowing the answers to questions, you might be wondering, where do I draw my authority from, right? Am I a professor of ignorance or something like that? Well, it's not that I have any special skills in ignorance, but I do want to celebrate and embrace our ignorance. Not the sort of cynical political ignorance that has, infected and perpetuated anti-elitism in our society, but an honest, open, scientific ignorance, an embrace of that, because in my view, ignorance is where the new discoveries lie, right? We can't make new discoveries unless we embrace that ignorance, unless we're willing to sail off into it in order to discover what remains to be found. And for me, it really started when I was a kid and I was reading about the Age of Explorers, and I thought, that was really cool. Because these guys and these women, all they had to do to discover something new was get in a boat and sail across an ocean, and they could potentially find an island that no human being had ever walked on before. They could put the first footprints on a beach, right? They could find a fruit and be the first person to ever taste that fruit. To me, that was really exciting. I mean, probably the first person to ever taste a fruit thought it was gross, right? But to me, it was exciting just to think that you were the first person to know something or to do something or to go somewhere. I mean, think of all the firsts in human history, who was the first person to see the Grand Canyon, right? Somebody got that, right? What a moment. Or the first person to eat chocolate, right? That's a good one. The first person to eat chocolate while looking at the Grand Canyon, right? These are all firsts in human history, and I wanted one. I wanted to be an explorer. But the more you're reading about the age of explorers, you realize it's hundreds of years ago, right? And thanks to Google Earth and satellites, there aren't any more islands for me to sail on and to discover new beaches where nobody has walked on before. And the more you grow up and learn also about science, you realize science really has a lot of stuff figured out. I mean, think of all the amazing things we have, right? We have these devices you can use to fly across oceans in just hours. You can download all of human knowledge into a tiny device that fits into your pocket, right? You can even email celebrities, right? This is about as close as I get to Brad Pitt, right? But you might be forgiven for thinking science hasn't mostly figured out, right? Because in your daily experience, you rarely find something that cannot be explained scientifically. I mean, 1,000 or 5,000 years ago, that was an everyday occurrence. It was very natural to have an experience, lightning, weather, whatever, that you couldn't explain, you couldn't understand. These days, the world around you seems well explained. So I think that most people feel that that science has just a few details to iron out and everything else we understand, right? So the point of our book, and the point I want to make to you tonight, is that the exact opposite is true. I think we're at the beginning of a new era of exploration, a new age of discovery when we're going to figure things out about the universe that will totally blow our minds. And to me, that's really exciting. So what am I talking about? Because there aren't any more islands for you to discover. I don't mean to lead you on. When I talk about making big new discoveries, I mean answering really big, fat questions about the universe, okay? And when I say a big, fat question, I mean a question you don't have to be a scientist to understand why the question is interesting. Not to mention understand the answer, right? The kind of question we all want to know the answer to just because we're human beings and we're curious. The kind of question where if you knew the answer, it might even change the way you lived your life or your whole vision of the human context. So let's be specific. What kind of questions are we talking about? You might be thinking about these kind of questions. Why are we here, right? That's a question everyone wants to know the answer to. Or what happens after we die? If you actually knew the answer to that question, what happens after you die, it might change the way you felt about your life or how you lived it, right? All right. The problem with these questions, of course, is that they're not science questions, they're philosophy questions. I love philosophy, it's a lot of fun, but hundreds of years later, thousands of years later, they haven't really made a lot of progress on these questions. And sometimes I wonder if philosophers are actually more interested in, the questions than the answers, or the process of debating them than the answers. Here's a famous philosophy question. What is it like to be a bat? Okay, now, this is not a made-up question. This is the title of the most widely cited philosophy paper of all time, okay? They're still discussing this and smoking banana peels and talking about it in the halls of philosophy departments, right? And they'll never probably get an answer. By the way, I've read the paper. The answer is, we'll never know what it's like to be a bat. All right, but the thing that's exciting to me is that there are other questions at the same gut level of importance that are science questions. Questions like this, right? Questions like, what is everything made out of? Or how did the universe begin? After all, the universe has one true history, right? The universe began in one way and in no other way. And if you knew that actual history, from the first moments to the next 10 minutes or 10,000 years, if you knew how it actually began, that very well might change the way you felt about humanity. The way learning that the Earth is not the center of creation, right, affects the way people think about the role of our lives and our importance. So to me, it's exciting because these questions have answers, and have answers that we will discover. In 1,000 years or 100 years, somebody will know the answer to these questions in an objective, scientific way that reasonable people can't disagree with. Imagine that, right? Those people will look back at us and they will wonder, what was it like to live in such ignorance, right? To not know the answer to very basic questions about our universe, right? The way we look back at primitive man and woman and think, how could they live in this world and not understand anything about their context? How could they look up at the stars and not even know they were stars, right? That's where we are today. All right, so let's dig into one of these questions. We don't have time to talk about all of them. This is the one that I spend my professional career working on. I'm trying to answer this basic question. What is the universe made out of? To me, it's a very simple question. It's a reasonable question to want to know the answer to, right? What am I made out of? What are you made out of? What is the organizing principle behind this whole ridiculous, beautiful universe we find ourselves in, right? I think it's also probably an ancient question. I think people have been asking questions since, people have been asking questions. And all you need to get inspired to ask this question is take two rocks and smash them together, and you get smaller rocks, right? And you smash those rocks together, you get smaller rocks, and you can keep doing this. And I literally remember doing this as a child, wondering, can you keep going and get infinitely small rocks, right? Or at some point, does it stop being rock and turn into something else? Or do you get to the smallest possible rock? You know, so maybe it's no surprise I became a particle physicist, but I think this is a simple question that everybody wants to know the answer to. How's this whole thing put together, right? So imagine that you are a caveman or cavewoman physicist up here, and you are tackling this question for the very first time, right? What is the world made out of? How do you even begin to address such a big question with limited tools, right? Well, in science, a very standard approach when you're tackling a really big problem is to just try the simplest thing first, right? If that doesn't work, then you try the second simplest thing, and you elaborate until you get something functional. So what's the simplest way to answer this question, what's the world made out of? Well, you might just start by saying what's in the world, right? Let's just like make a list of what's in the world, okay? And because it's caveman, cavewoman times, right, your list is going to look like this, right? I'm in the world, you're in the world, there's a rock here, there's a rock there, right? There's a bunch of different rocks in the world, right? And you're going to quickly discover that there's a lot of problems to this approach, right? Problem number one is there's more than just rocks in the universe, right? I mean, if you want to explain everything that you see, you want to answer the question, what is the world made of? You can't just explain rocks, you have to explain all the complexity that we observe, right? And the more you look around you in the universe, the more you're amazed at the complexity. I mean, we have like bicycles and ice creams and strangely muscular fellows becoming governor of California. Like, it is a weird and beautiful universe that we live in. And if you want to answer this question, you have to explain all of it, right? Now, so think for a moment about the kind of answer we want, right? You don't want a list. Like, if I knew the answer and you asked me, Daniel, what's the universe made out of? And I gave you a list of everything that's in the universe, you wouldn't feel satisfied. You wouldn't go, aha, I get it, yeah, right? There's no insight there. Because the kind of answer you want is not a list. I mean, we're not botanists, right? We want to peel back a layer of reality, right? And explain all this complexity in terms of something simpler underneath. We want to peel back everything we see and find out how things really work underneath. That's the kind of answer we're looking for. Not a technically sound answer, but an insightful answer, right? So how do we get there? We don't just make lists. That's not a way to make progress. What you do is you organize your knowledge, right? And then you look for patterns. So, we group everything together, and you can argue, does Arnold belong in the rock category or the living thing category, whatever, but you make categories and you notice patterns, right? And those patterns lead to questions. Why is this way? Why is all this stuff green? Why is there more of this and why is there more of that, right? And those questions are your clues that are going to guide you to revealing that deeper layer of reality. That's going to let you peel back and see the explanation that lies underneath, right? So let's fast forward a few hundred years or a few thousand years if you think the Greeks get any credit. Personally, I don't think they should. And you can explain everything that you've ever seen or touched or tasted or sat on or tripped over. Anything any human has ever interacted with, we can build out of just the elements of the periodic table, right? Now you might be thinking, well, this guy is a particle physicist. Why are we hearing about basic high school chemistry, right? Well, yeah, it's high school chemistry. But in my view, it's also one of the most underrated intellectual achievements of all time. Why? Well, if our goal is to explain the nearly infinite complexity of the universe, right, we boil it down to about 100 objects, right? We want to go down to like 2, 3, or one particle. We're most of the way there already. The hardest part is going from almost infinity down to a small finite number, right? So to me, this is really amazing. And it makes me wonder, like, why is it even possible? Why is our universe organized in this way, where all the complexity we see around us, strawberries and hamsters and blueberries and stars, all that stuff can be made out of just a few basic objects, right? It's like the universe is organized by the Lego company, right? I mean, that's the principle behind the Legos, right? With a few basic objects, you can make anything, right? Why is the universe that way? We don't know. We have no idea. We happen to live in a world that follows the Lego philosophy. I'm grateful, because without that, particle physics would be much more difficult. I mean, imagine a universe where every object is made out of its own kind of particle, right? Every single thing, like cats are made out of little cat particles, and that's why they're so weird or something, right? I mean, we could have lived in that universe. If you are a caveman or cavewoman physicist, and you are open to any crazy new idea, you have to consider that also, right? But we don't live in that world, right? We live in a world where reductionism seems to work, and we're able to explain everything that we've seen in terms of just the stuff in the periodic table. Okay, but we don't get to the periodic table and say, here's 100 elements, we're done, right? That's a list. Lists are not insightful, right? So we organize our knowledge, and of course, when you do, you discover there are lots of patterns in the periodic table. It's, after all, it's periodic, right? The stuff on the left has some sort of characteristics, and these guys are over there, and those guys are metallic, and there are definitely patterns here, and those patterns lead to questions, right? Why is this way? Why is this that way? Why is there a hole here? This kind of stuff. And those questions, of course, lead us to do experiments, and they're the clues that help us reveal what's going on in the periodic table. Because, of course, all the structure we see in the periodic table, all these things, the metallicity and the active nature of some of these objects and the inactive nature of others, is just due to the structure of the atom, right? So that's the lesson. I'm not telling you this because I think you don't know it. I'm sure you do. The point I want to make is that this approach works. Organize your knowledge, right? Look for patterns, ask questions. In this case, it directly reveals that because it's the way the electrons fill in these orbitals that determine the behavior of all of those elements. And the number of protons tells you which element you're in. So all the structure of the periodic table, all of those clues, were in fact pointing to the structure of the atom, right? So this approach, we hope, will guide us even further as we try to drill down and pierce the veil of human ignorance to understand what's even lower, what's even deeper in terms of what matter is made out of. So let's drill further, right? Inside the atom, we have protons and neutrons in the nucleus. Surrounding that, of course, we have electrons. And inside the protons and neutrons, we have quarks, 2 down quarks and an up, or 2 up quarks and a down, and you have protons and neutrons. And that means something sort of incredible. It means that with up quarks and down quarks, with which you can make your protons and neutrons, and electrons, you can make any element of the periodic table. Wow, right? 3 particles to make any element of the periodic table to make anything you've ever eaten, right? So don't ask a particle physicist to write a cookbook because every recipe will have just 3 ingredients in it, right? Right? And it's amazing to me that we live in a universe where, again, the complexity arises not from the innate complexity of the objects, but just in the arrangements of those objects, right? The tricky thing about a recipe, of course, isn't getting the up quarks, the down quarks, and the electrons, though you can't really buy those in the bulk food section. It's in putting them together in the right way to make a chocolate cake, right? Or a roast chicken, right? All the same basic ingredients, totally different flavor. All right, so you might be thinking, well, we had almost infinite complexity. We boiled it down to the periodic table, about 100. Now we're down to 3 particles. These guys almost have it figured out, right? Maybe next year we'll be hearing about the 1 particle that rules them all, right? Well, you'd be forgiven for thinking that's true. That certainly seems to be the projection. But it turns out the story is a little bit more complicated because there are more than just these 3 particles out there. So the up quark and the down quark are members of a group of particles. There's 6 of them we call quarks. There's also the charm quark, the strange quark, the top quark, and the bottom quark, okay? I was not on the committee that named these particles, so I have no responsibility. Who wants to be a bottom physicist anyway? And then there's the electron, which is an example of a particle we call leptons, and there's 6 of those as well. So here we are at a list again, right? But we don't get any insight from making a list. What we do is we organize our knowledge. And so here I've organized it into a new periodic table, but this is the periodic table of the fundamental particles, right? But the same approach applies. Look for patterns, ask questions, and we hope that those questions will reveal what's going on underneath. But now we've arrived at the current state of knowledge, right? As far as we know, these 12 matter particles make up everything that we've seen or tasted or touched or sat on, right? And we don't know what lies underneath. But there are a lot of really intriguing clues, a lot of really interesting patterns that I hope will guide us to figuring those things out. So let's take a little tour. Here we have the up quark and the down quark, which you're familiar with because they make up U. And then here's the electron, which you also need to make up U. In this column, we also have the neutrino. Okay, neutrino is a really weird little particle. Not weird because it's rare. In fact, they're everywhere. There's 100 billion neutrinos passing through my fingernail every second. 100 billion with a B, right? Why don't you feel them? Why am I not like beaten down by all the neutrinos? Well, the answer is they ignore us. They pass right through us without even noticing. Neutrinos can pass through a wall without noticing. They can pass through a wall made of lead. They could pass through a wall made of lead that's a light year thick and not even notice. because they hardly ever interact with our kind of matter. And that's just a clue that tells you there's a lot of stuff out there that you're not perceiving, right? The way you see the world is not the way the world is on a more fundamental level. Now, the really interesting thing about this table is we have these 4 particles in the first column. All the other particles that round out the 12 fall into these categories where we can line them up in rows. We put the charm quark here next to the up quark because it's basically a copy of the up quark. It turns out it's exactly the same as the up quark. It has the same charge, it has the same spin, almost the same interactions. The most important distinguishing feature is that it's heavier, right? As we go this way, we get more mass. The top quark is just another heavy version of the up quark. It's like the up quark has these 2 secret fat cousins that nobody told us about, right? Why are they there? We don't know. We have no idea why the charm at the top even exists, and not just why do they exist, but why are they just copies of the up quark? The really incredible thing is that every particle in this first column also has 2 copies, right? The strange and the bottom are just copies of the down quark. The muon and the tau are examples of heavy versions of the electron. There's even 3 of these neutrinos, right? Though their mass relationship is a little bit more complicated. So I look at this table and I have questions, right? These questions like, what are these particles for? We only need 3 to make matter. Why do we have 12? Are there only 12? Theoretical physics puts no limit on the number of particles that could be out there. It could be 12, so we could be looking at the whole ice cube, or this could be just the tip of the iceberg. There could be 12 million kinds of particles out there that we haven't even discovered, right? To me, a really interesting question is why each particle has 2 copies. And it sort of goes to the question of seeing numbers in mathematics. I think numbers are really interesting. And remember that one of the goals of physics, the stated goals of physics, is to describe the whole universe, right? But to do it in a simple way. So imagine physics is concluded when we have a single equation that describes the whole universe. And maybe that equation is small enough it fits onto a t-shirt, right? That's the standard. Okay, so imagine you have that equation. You're looking at it, and there's a number in that equation, like 7. If the fundamental equation of the universe has the number 7 in it, that means the universe is 7-ish, right? Or there's something deeply 7-y about the universe, right? You can extract real insight from looking at those numbers. So when you see a number in physics, you have to ask why. So I see this, there are 3 columns, and I think, why 3? I mean, you go and you ask theoretical physicists and mathematicians, what numbers do you expect to see in a theory of the universe? They say, 1, pi, e, right? Nobody says 3, okay? Unless they're Catholic, which, and maybe they have something there, So to me, this is a clue, right? It suggests that maybe these particles are made out of smaller particles that are just arranged in different ways, and there's 3 kinds of ways to arrange them or something like that. It's so obviously a clue that something interesting is going on underneath, right? We can recognize that it's a clue. We just don't know what that clue means. It's screaming at us, clue, clue, clue. It's the kind of thing where in 200 years, physics undergrads will read about this in textbooks and say, oh, it was so obvious. If I'd been a physicist in 2018, I totally would have figured that out, But here we are at the forefront of human ignorance. We have no idea what it means and which direction to take it. We know it means something, right? So it's tantalizing and frustrating. Another question is, why do the particles have all different masses? We know that the Higgs boson is responsible for giving mass to the particles, but we don't know why it gives some of them a huge amount of mass and some hardly any at all. The Higgs mechanism doesn't explain that at all. There's no answer for that. That's a huge mystery. One of my favorites has to do with these charges of the particles. So the electron, of course, is charge -1. And the quarks have these funny fractional charges, plus 2/3, minus 1/3, right? They're really weird little charges, except that when you add them all up to make a proton, you get charge +1, which is very nice. Because if you have a proton and electron, you get a neutral atom, and that allows things like chemistry and biology, silly physics books and cookies, and everything you like about the world relies on this balance, right? The problem is that in our theory of the standard model, the charge of the leptons and the charge of the quarks are totally unrelated knobs. Okay, so you're like at the control panel of the universe. You can dial these things to whatever you like, right? Now, some physicists think they have some understanding of why these knobs have to be set a certain way, but it also seems like it might just be a huge coincidence, right? But it would have to be a massive coincidence, like not a coincidence like on the size, on the scale of the sun and the moon being the same size in the sky, right? That's a very nice coincidence because we get eclipses, but that's a coincidence at the 1% level. If these two things can have any value but happen to balance each other, that's a really, really deep coincidence, right? Or it's a clue. It's a clue that there's a connection between the quarks and the leptons that we don't quite understand, right? They're two sides of the same coin in some interesting way, or they're built out of the same little particles in some way, right? And so this is the kind of thing that I hope will help us understand. And so we have a pretty good model of physics, right? Here's the equation for it, right? And you might be wondering, like, it works pretty well. It describes experiments pretty well, Have we made enough progress that we could fit it onto a T-shirt? I mean, if you can get like 1-point font, then you certainly can. And sometimes I think that we're just sort of looking at this problem the wrong way. That if we just like spoke a different language or developed a different math or even had a different mathematical notation, it would all of a sudden make sense. Like this is one of my favorite Far Side cartoons. These guys don't understand Spanish, so they're forced to write down what the dolphins are saying phonetically, right? Whereas, of course, if they spoke Spanish, oh my God, what could they learn about the life of a dolphin, right? Okay, so I've been telling you about the open questions about all the stuff around us, me and you and hamsters and all these things, and there are really big, basic questions about how that works. But the biggest problem in answering the question, what is the universe made out of, is that most of the universe is not made out of any of this stuff. Those 12 matter particles I described and all the things around you turn out to be a tiny slice of the universe. Less than 5% of the stuff in the universe is everything you're familiar with and everything every human has been familiar with. So we've been doing science for hundreds of years, getting a fine understanding of matter. Turns out to be relevant only for a tiny little slice of the universe, right? And now you might be thinking, man, a minute ago, I was ready to congratulate particle physics on almost having it figured out. We were down to just 3 particles, right? And now we're like, oh, this is disappointing. But it's not disappointing, it's exciting, right? It's exhilarating. Because for the explorer in me, this says 95% of the universe has not been explored, right? There are continents out there to land on. There are new beaches to walk on. Most of it has not been figured out. To me, that's exciting. That's exhilarating. That's why I think the best part of science is our ignorance, right? The things we don't know, because it's in there that there's room for me and younger people and your kids and your kids' kids to make incredible, mind-blowing discoveries about the way the universe works. Okay, so what is this big chunk of the universe, and how can we possibly know? It turns out we know it very precisely. We've measured very precisely how much we know about the universe. It's like we're in an era of precision ignorance, right? We can measure very accurately how much we know about the universe. So people figured out that there's more to the universe than what we can see, and there were a couple of really important clues. One came when they were looking at how galaxies rotate. So our star is a part of a galaxy, the Milky Way, which is rotating, a totally normal thing for a galaxy to do. And all galaxies rotate. And we can look up at the sky, and we can see them rotating, and we can measure their rotation. And you can think of a galaxy sort of like a giant cosmic merry-go-round with a bunch of ping-pong balls on it, right? But what happens if you spin a merry-go-round with ping-pong balls on it? Well, the ping-pong balls are going to fly out, right? So in the case of a galaxy, the reason the stars don't fly out into intergalactic space is that there's something holding them in. That's gravity. So now we can do something cool. We can say, let's measure how fast the galaxies are spinning, and then let's add up all the stars and figure out how much gravity there is in those galaxies. And we can ask, is there enough gravity to hold those galaxies together, right? And this is a classic thing we do in science, is measure something in 2 different ways and see if it checks out. 99.9% of the time, it checks out. It's a total yawner, and we move on to something else, right? But sometimes you get a really weird, really interesting result. And that's what happened here, is that they measured how fast these galaxies were rotating, and they were rotating way too fast. There's not nearly enough gravity from the stars we can see to explain why they're not being torn apart. But the galaxies are not being torn apart. They're not throwing stars into intergalactic space left and right. We're pretty safe. And so this was a big puzzle for a long time. And people said, how can we explain it? So they came up with this idea of dark matter. Dark meaning we can't see it. Matter meaning it gives gravity, okay? So this is a classic physics approach, right? Something happens you don't understand. You give it a fancy sounding name, right? So you can like write grant proposals about it. But dark matter is a fancy sounding name. It's also basically all we know about it, right? It's dark, we can't see it, and it's matter, right? It's nicer to call it dark matter than to call it invisible gravity giving thing, right? But that's basically what it is, okay? And so they said maybe there's some other matter in there that we couldn't see that's also contributing gravity, and that could explain why these galaxies are being held together, right? There's something invisible in there. So let's talk for a moment about what it means for something to be dark. When we say dark, we really mean not that it's mysterious or bad in any way, right? Just that we can't interact with it. So particles have 4 ways to interact that we know of. One is gravity, right? Anything with mass is going to feel gravity. Another is electromagnetism. That's responsible for light. Anything that gives off light or reflects light is going to feel electromagnetism. And then there's the weak and the strong forces. These are responsible for breaking up the nucleus and for holding it together. So this is how the particles interact, and this is why we call dark matter dark. Because as far as we know, dark matter feels gravity, right? That's how we discovered it. We invented it, the idea of dark matter, to explain the missing gravity, right? But we think it doesn't feel electromagnetism because it doesn't give off light or reflect light. And we think it doesn't feel the weak force or the strong force. We've looked for it interacting in this way. Right? So as far as we know, the only way to interact with dark matter is through gravity, right? I mean, I've tried, but it's just totally ghosted me on social media, which makes it difficult because gravity is really weak, right? Gravity is the weakest of all the forces, and it means that in order to interact with it, you need enormous blobs of dark matter. It's very hard to do experiments with dark matter like a handful of dark matter. You need like a cosmic-sized blob of dark matter in order to even feel it, right? And the incredible thing about this discovery is that to explain how the galaxies are rotating, you didn't have to add just a little bit of dark matter, right? Like 1% or 2% of the stuff in the galaxy. You had to add an enormous amount because the galaxies were spinning really, really fast. So if 5% is the stuff we know, there's 5 times as much of that, there's 5 times as much dark matter as there is the stuff we know, right? Which is, again, humbling because we spent all this time understanding it. Then it turns out there's a lot more matter in the universe that's a totally different kind, right? This we call normal matter is not normal at all, right? It's abnormal, it's weird, it's unusual, right? Of course, we have a special affection for it, but it's not typical. So 5% of the stuff in the universe is stuff we know, 27% is the stuff we call dark matter, right? What about the, but before people would believe that a huge chunk of the universe was this new invisible thing. I mean, in order to just explain this one gravity rotation experiment, it seemed awfully convenient to postulate a new, invisible, never before seen bunch of particles that fill the universe, right? So before people believed that, they had to see dark matter in some other ways. And one way is through gravitational lensing. So dark matter is dark, you can't see it, and light can pass through it, but it has matter, so it can affect the shape of space itself. It can act like a lens in the sky by bending space. So imagine, for example, there's a huge blob of dark matter between you and some galaxy far, far away. What happens to a photon from that galaxy? Well, if it shoots out in this direction, it can get bent towards your telescope by this dark matter. Another photon shooting out in another direction can also get bent towards your telescope, right? So what does that mean? It means if you look up in the sky, you can see the same galaxy twice in the sky. Whoa. So either you've been smoking banana peels with the philosophy department for a little too long, right? Or there's a massive lens in the sky. And if you haven't seen this before, gravitational lensing, you should do a Google image search on it later. It's incredible. It's actually kind of beautiful. And you can see this in the optical. So it's really impressive. You can even see optical distortions. It's quite impressive. So that's a way we can see where dark matter is. We can use it sort of to map the sky by looking at how it distorts the galaxies that are behind the dark matter. But the biggest piece of evidence in my book for dark matter comes from a collision. So I'm a particle physicist, and my go-to strategy for understanding something is take 2 and smash them together, right? So don't ever ask me to fix your iPhone for you, right? Not a good idea. And but if you want to understand like galaxies, that this approach doesn't really work. Okay, I mean, I've asked the NSF for money for a galaxy collider, but I never heard back. But astrophysicists have a different approach. They don't build experiments as much as they just look out into the universe and find what's already happening, because the universe is huge and filled with crazy stuff, right? So they got really lucky and they found this collision of 2 galactic clusters, 2 clumps of galaxies. Now, each galactic cluster has normal matter and also big blobs of dark matter, okay? So what happened when these 2 things collided? Well, it was pretty spectacular. The normal matter slammed into itself, big explosions just like you would expect, right? The dark matter mostly passed through because it doesn't interact with itself and it doesn't interact with the normal matter. It just passed right through. Now, there is gravitational interactions, but that's way too weak to slow it down. And we can see the dark matter came out on either side because we can use gravitational lensing to see it there, and we can see the normal matter here. And this tells us something really important and deep. It tells us that the gravity from the dark matter is from its own kind of matter. Some people thought, oh, maybe dark matter is just a misunderstanding of the way gravity works, or a different way that gravity can operate. But this tells us that dark matter really is its own thing because it got separated from the gas and the dust and all this stuff that got stuck here in the middle. It got separated so we could see it had its own gravity. It really was its own thing. And that's why we're confident calling it matter, because we think there is some stuff there, right? Something that's giving that gravity. But what is dark matter, right? We know it's dark. We know it's out there. We know there's a lot of it. That's about it, right? And so one leading theory of dark matter is that, well, maybe dark matter is made out of a particle. Okay, sure. And the leading candidate is called a weakly interacting massive particle, which stands for WIMP, right? And maybe dark matter is a particle. I don't know. Maybe dark matter is something else. My personal fantasy is that dark matter could be made out of something totally different. I mean, from my perspective, it's dangerous to extrapolate from 5% of the universe to a huge chunk of the universe, right? Maybe dark matter is totally different. Maybe it's made out of a kind of matter which isn't made out of particles. I would love that kind of discovery because it would change the way we look at the universe. Or maybe dark matter is made out of not just one particle, but many particles, right? And maybe they have some new kind of interaction we're not aware of. And there could be dark physics and dark chemistry and dark biology, right? There could even be dark people for all we know, right? Somewhere out there could be a dark physicist giving a dark lecture to a dark audience, right? Saying, we understand 95% of the universe, right? So here we stand, right? 5% of the universe is stuff we know. 27% is this weird stuff. It's called dark matter. We have lots of ways to see it. We're pretty sure it's there. We don't yet know what it is. What about the rest of the universe, right? If we're going to pretend to answer the question, what is the universe made out of, we have to explain at least half of the stuff in the universe, right? So this last 2/3 of the stuff in the universe is something we call dark energy, okay? But dark energy is science code for we have no clue what this stuff is, okay? And the only relationship between dark matter and dark energy is literally the word dark, okay? So how can we possibly understand this? Well, people discovered dark energy was a thing when they were thinking about the history of the universe and the universe's future. So here's a brief primer on what has happened so far in the universe. Things began with a big bang, right? So time zero, you have a huge explosion, right? Things fly out. And then structure forms and interesting stuff happens, right? You get cats and galaxies and all that stuff. But a question was, what's going to happen next? And there were various possibilities people were debating. Possibility number one is that there was enough stuff in that explosion, enough gravity, that things would slow down, stop, and then fall back in, right? To like a big crunch, okay? A possible fate of the universe is everything crunches back in. And don't worry, that would be in billions of years, so you still have to pay your tax return and all that stuff. Another possibility is that there isn't enough stuff in the universe to slow it down and turn it around, but it just sort of generally drift out forever, slowing down and cooling off forever, but never turning around. Okay, and this goes by the name of the heat death of the universe. So people went out to measure this, and they figured out a really cool way to see how the universe was expanding, so they could differentiate between these two different scenarios, right? And they used this special kind of star called a type 1a supernova to figure out how fast the universe was expanding. And they went out and they did this experiment, and the universe came back and it said no to option A, no to option B. The universe went for secret option C, okay? And I love when the universe goes for secret option C, when it's like, humans, I'm going to blow your little minds, okay? And blow our minds it did, because it turns out what's actually happening to the universe is that about 5 billion years ago, something happened, and the universe started, instead of slowing down after the Big Bang, started to speed up, right? It's accelerating. So things are getting further away from us faster and faster every year. What? And we're talking about accelerating galaxies, right? Hundreds of billions of stars being pushed away from us. That takes a huge amount of energy. I don't know, maybe 2/3 of all the energy in the universe, right? And the thing about dark energy is that we have no idea what dark energy is, right? Why is everything running away from us? We have no idea. All we have is this observation. We've seen that the universe is expanding, and that expansion is accelerating. There must be something that's doing it. We don't know what it is. We don't know why it's doing it. We don't know what the plans are, right? Which makes it very hard to predict what's going to happen at the end of the universe, right? We don't really know. But I like to think about various scenarios. I mean, imagine if dark energy continues, okay? The thing you need to understand about dark energy is that not only are things moving away from us, but new space is being created between us and other galaxies, okay? New space is being created. What does that mean? Well, imagine a photon being shot from a galaxy towards us. New space is being created faster than those photons can fly through that space, which means those photons will never reach us. It's like if Usain Bolt was running towards you and somebody's laying track in front of him faster than he's running, right? He's never going to get to you. It's the same case with these other galaxies. Something is not just expanding, not just pushing things through the universe, but actually creating new space. And that means that those galaxies at the edge of our observable universe are disappearing. They're falling off the edge of what we can see. They're getting pushed away from us. We used to be able to see them. Now we can't, right? The universe is getting more and more further apart, and it's doing it faster than the speed of light, right? It's not breaking the law of relativity, because nothing is moving through space faster than the speed of light. Relativity doesn't prevent you from creating new space at any speed, right? So take that to its extreme, right? Galaxies start to disappear from the night sky, it gets darker and darker. Dark energy continues, it might even shred the Milky Way, right? And eventually stars will begin disappearing, right? The future of astronomy might look like this, right? I mean, in my optimistic days when I think astronomy even has a future, after the next 4 years of this government, but imagine being an astronomer, 3 years, thank you. Imagine being an astronomer, maybe less than that. Imagine being an astronomer in 10 billion years, and you're looking up in the night sky and this is what you see, right? How would you have any chance at unraveling the secrets of the universe, right? It's hopeless. Now, before you feel too good about living in the now, remember, we're 14 billion years into the universe already. What used to exist in the night sky a few billion years ago that's now gone forever? Well, we have no idea, and we never will. Okay, so where do we stand? Well, here's a pie chart of the universe, okay? Most of the universe is something we only recently discovered we don't know anything about. That is so humbling / exciting, right? That to me is wonderful. It's like, wow, such big questions to be answered, right? A huge chunk of the universe is something we know is there. We know it's dark. We know it's matter. That's about it, right? And the rest of the universe is me and you and physics books and all sorts of silly stuff, right? We are really the et cetera in the universe. We're really the leftovers, okay? And we have to wonder what things that we've learned about studying our environment we've overgeneralized. What basic assumptions have we made because we've been looking at a particular kind of thing that we think applies to the whole universe but doesn't really? You know, imagine you're an elephant scientist, okay, and you spend 300 years studying the elephant's tail, right? And you have a really elaborate tail theory of the elephant. And then somebody walks you around to the front of the elephant and says, actually, maybe you should consider meeting the rest of the elephant, right? So if you're a physicist, you're probably going to say, well, I'm going to model the elephant as a linear combination of tails or something, right? You might think, well, that's a really dumb idea, right? There's no way you can describe the elephant in terms of a bunch of tails. That's the same argument I made 10 minutes ago when I said, maybe dark matter is made of particles, right? After all, everything we've seen is made of particles, so why shouldn't dark matter be made of particles? My point being is just that it's dangerous to extrapolate and to hold too tightly on what we think we know. Because I think the future of physics contains crazy revelations, you know? I think this means that there's the potential here for a real revolution in the way we think about physics. You know, revolutions on the scale of quantum mechanics or relativity. The kinds of discoveries that really just, you know, blow your mind, okay? Imagine getting to read a child's astronomy book from the year 3000, right? What secrets would that contain that children, 6-year-olds in the year 3000 would think are obvious, right? We have no idea what those are, and I hope we live long enough. Now we're doing everything we can. You know, we have amazing technology. We have space telescopes and gravitational wave detectors, and we have amazing particle detectors underground to try to answer these questions. And I like to think that maybe these are the golden days of physics. Maybe we're going to figure this stuff out in the next 5 or 10 years, and then people will look back on these years and think, wow, I wish I had been a physicist in 2018 or 2019 when they really cracked some of those big secrets. But that remains to be seen. So in the book, we talk about lots of these questions. What is the universe made out of? What is dark matter? But I think it's also amazing that there are other questions sort of at the same level, like really basic, simple questions that we don't have answers to. Questions like, you know, what is space, right? You might think, oh, well, that's easy. Space is emptiness. Space is nothing. Space is the backdrop that the universe, the events of the universe play out on, right? But space does things that we're sure nothingness can't do. For example, space can expand. That's what dark energy is. It's the expansion of space. Space can bend, right? Einstein tells us that gravity is the bending of space, right? Space can even ripple, right? These are gravitational waves. We've seen this happen, okay? So we know that space can do things that nothingness can't. This one's a joke, by the way. Although sometimes I wonder if that's appropriate because space can do so many other crazy things that's not always so obvious. The thing is that we've only recently discovered that space is a thing. It's not emptiness. It's a dynamical physical thing with interesting properties, probably properties we haven't even discovered. It's like we're fish scientists and we've been swimming around in water for 1,000 years, ignoring the water, right? Thinking, oh, it's nothingness, it's just the emptiness, right? That's what we've recently discovered. Another really basic question is this one. What is time, right? We think time and space have an intimate relationship, and relativity tells us that there's some connection there, but there's also important differences, right? I can move through space however I like, but I can't move through time however I like, and I can only just march forward at 1 second per second, right? Why is time so different? Why is there only one dimension of time? Why does time flow this way and not backwards, right? Really simple, basic questions we don't have answers to. Or how many dimensions are there of space anyway, right? You're familiar with 3, right? Forward, backwards, left, right, up, down. But people think there might be other dimensions, little looped, curvy dimensions that you can't detect. There could be 11, there could be 26, right? This is a very basic feature of the world, right? You're a conscious being in the world, you want to understand it. This is a pretty simple thing to want to understand. So I wanted to focus tonight on these questions. Instead of telling you all the things science has figured out, I wanted to share with you my enthusiasm for all the things science hasn't figured out, because I hope that means that I've given you a guide to what science will eventually figure out. So thanks very much for your attention tonight.
Thank you very much, Daniel, for such a nice talk. I think we can entertain some more questions. Raise your hand.
Okay, I'm going to go back to your first slide,
Awesome.
where you were differentiating between philosophy and science. But what is science?
Have you been holding this question since then? I'm really impressed.
Yeah. What is science but the answers that the philosophers were asking in the past? I mean, just to use your example that you had, you think science can never explain where we go after death? Why is that just not a science question we haven't answered? Why are you putting that somewhere unanswerable?
So what is science? Science is more than asking questions. Science is a system of accumulating knowledge about the world, right? And so some questions we can't accumulate knowledge about, like what are things made out of, or what's under that rock? You know, those are questions we can use science to answer. Other questions we haven't yet figured out how to use science to answer. Doesn't mean we never will. Some questions used to be totally unassailable scientifically, and now they aren't. You know, the sort of like the universe is expanding, so does our scientific understanding of it as well. Questions which used to be philosophy are now science, and today's philosophy questions might be tomorrow's science. I mean, some of those tricky ones I'm not sure about, but there are some questions that that we can't answer today that we can develop new technologies to answer in the future, absolutely.
Other questions? Excuse me.
Can you tell us how physicists calculate the vacuum energy and interpret the results for us?
Sure. So some people think that one explanation for dark energy is that empty space itself has some energy, so the energy of the vacuum. And we know that space itself is never really empty. It's full of virtual particles, and there's the Higgs field and all sorts of stuff. But they sit down, they try to calculate this stuff, and I'm not a theorist, so I can't get into the technical details for you. But I know that when they sit down, they try to calculate how much energy there is in empty space and compare it to the energy you need for dark energy. Those two numbers disagree. And they don't disagree by a little bit. They disagree by 10 to the 60. Okay, so people have some ideas what dark energy might be, but those ideas don't really work at all yet. So we're in the very early days of just building kinds of ideas that might lead to eventual ideas that might lead to real models that describe what dark energy might be. We're still stumbling around in the dark.
10 to the 60?
10 to the 60, yeah. It's not off by a little bit.
So with the when you turn matter into energy, or the other way around, you get this thing out called a photon. And I didn't see that on your chart. Kind of relates to it a little bit. So that's one part of the question. And the other part is you mentioned that dark energy doesn't relate to electromagnetic energy, but I've heard somewhere around the block that the photon has got something to do with electromagnetic energy, and we're bending light. We are relating to it, gravity. Can you shed some light on that?
Sure. All right, so your first question was, why didn't I describe the photon and those other particles when I was talking about what the universe is made out of? Well, you're right, the photon is a particle, but when we talk about the particles that make up matter, we talk about these 12 particles. The other particles, the photon, the W, the Z boson, these explain forces. So electromagnetism, the weak force, the strong force, all those forces I described also have a particle associated with them, but they're not matter particles in the same way. That's why we make that distinction. And then your other question was, is the photon related to dark energy? Because the photon is affected by to dark matter, because the photon is affected by mass and dark matter has mass. So yeah, there is some sort of interaction there, but we don't really understand gravity in a way that we can use it to calculate interaction with photons, because we don't have a quantum mechanical theory of gravity. We have this theory of gravity as a bending of space, but we don't have a theory of gravity as emitting particles that we can think of as forces that interact with the photon. So we're not there yet.
In several of the lectures, we've heard discussion about quantum entanglement and non-locality action, spooky action at distance. What does that indicate about our understanding about reality?
I think it's really interesting that we look out in the world and we try to understand it. And so far, the world seems to be understandable, but we discover a lot of weird stuff about the world. And one of the things we discovered about the world, the universe, is that it seems to be kind of local, that you're only affected by things around you, right? So for example, we have the speed limit of information, the speed of light. If scientists on Alpha Centauri develop a death ray yesterday, they can't kill us with it immediately, right? So we're sort of protected. There's only this bubble of local stuff that affects us. Why, you might ask, reasonably, why is the universe local? Well, we don't know. We have no idea. We think the universe has to have a speed limit for reasons relating to how time works, but we don't know why the speed limit is what it is. And you can imagine a universe where the speed of light and the speed limit of information was much smaller, right? We don't know why the speed of light is just a number. It could have been anything as far as we know. So the universe could have been much more local, or it could be much less local, which means like travel to other stars could have been even easier, but also death rays from Alpha Centauri could have arrived momentarily, right? So I don't know why the universe is local, but it seems to be, and I'm sort of glad that it is.
How many cats do you have?
My daughter is sadly allergic to cats, even though she loves cats, so instead we have rats, which are actually very smart little creatures. I actually think rats are smarter than cats.
I want to ask you about, so in the beginning of the Big Bang, you had the separation of forces from each other. I think that's the modern interpretation of how that was.
Uh-huh.
Is it reasonable to postulate that perhaps dark energy is perhaps a separation of yet another force from those forces, and that we are simply seeing a continuing, perhaps like quantum fluctuations where these things are now just happening. Maybe they're, who knows, a billion years from now, 10 billion, 5, who knows, 20 billion. Some new force enters the picture and completely alters our understanding, and what are the probabilities that something like that could be predicted?
Well, if you want to say, is it reasonable to say dark energy might be X? You can put almost anything in X, and the answer is yes, because we have such little understanding of what dark energy is. We don't understand what it is. We don't understand why it turned on 5 billion years ago. We don't understand if it's going to keep going, if it's going to stop. So all the ideas you proposed are things people are thinking about, but nobody really has any concrete ideas, unfortunately. So probabilities as to what's going to happen in the future, totally premature to even be thinking about that kind of thing. I mean, we still can't even predict the weather next week, right? So, The universe is even more complicated.
Any other questions? Oh, there was one more here. Okay.
I can just spark it out. Ever since you said about the Earth, Moon, and Sun relationship being a coincidence, having gone out and seen the hundreds of pounds of totality last year.
Good for you.
Can you just talk to me about that for a second? Because that's stuck in my head hard. It still blows me
Sure.
away. But it seems to pass over you like it's not a big deal.
So the question is, what does it mean that the sun and the moon are the same size in the sky, and that's a coincidence? So in order for us to have eclipses, right, both solar and lunar eclipses, the sun and the moon have to be the same optical size in the sky, right? In our sky, they have to take up the same area so that the sun can block the moon or the moon can block the sun, right? How could that happen? Well, either the sun and the moon can be the same size and the same distance from us, so they take up the same space, but that's definitely not the situation, right? The sun is much bigger than the moon, enormously more vast, but also more distant. And it just so happens that the ratio of those two things is the same for the sun and the moon. So the sun, even though it's much bigger, happens to be just far enough away so it appears the same size as the moon in the sky. Total coincidence. Now, to me, that's really interesting because, and I saw the eclipse also last year, and I was really amazed by it, and I thought, what did primitive man or woman think looking up at this, right? Like, wow, this seems like an important piece of information about the way the world works, right? Turns out it's not, you know? I mean, it tells you something about how the objects are arranged in the sky, but it seems like an important piece of information that they're the same size, but that's really just a coincidence. The moon could have been twice the size, right? And we could only get one kind of eclipse, or could have been only half the size, and we get no eclipses at all, right? So that's just a coincidence. We don't even understand how the moon was made, you know? It's maybe torn out of a big chunk of the Earth when something collided into it. And that affected how big the moon is, right? But like, there's no reason the moon has to be the size it is. And it's an unusually large moon for our solar system, right? I hope I answered your question. All right.
So I have a philosophical physics question.
Awesome.
Just curious, you're saying you like to explore things and all of that, but why do you feel it's important to get down to that level and discover what the particles are or what makes things up? Why do you feel that's an important thing to pursue?
Why is it important? Why is it interesting? I mean, imagine that somebody had the answer on a piece of paper in a box and it was closed and put it in front of you. How long could you wait before you opened that box? I think it's an innate part of being human to be curious about our world and want to know how it works, especially when you discover that the world around you doesn't work on a microscopic level the way you thought it did. You know, things that we see around us, rocks and llamas and blenders, these are not basic principles of the universe. The universe operates on different rules that we can discover. To me, that's like a drug. Like, I want to know the secrets, you know. I think it's just a part of being human to want to know how things work.
Thank you very much, Daniel.